Location isn't the only thing that determines what part of the electromagnetic spectrum a telescope can observe. Both the telescope and the detectors used with it also define the type of light the telescope can detect. This is important because the type of light being observed will determine the type of object that can be seen. So I'd like to give a quick summary of the sort of objects observable in each part of the spectrum. If you don't remember what all of these things are, this might be a good point to go back to Chapter 1 and review the vocabulary for objects in the universe. We'll also be looking at most of these in more detail later in the course. Visible light is in the wavelength range from 400 to 700 nanometers. Most astronomical observing is done in the visible spectrum, and until the 1930s, this was the only kind of astronomy done. Visible light telescopes span the range from small amateur scopes up to large professional instruments like this telescope on Mount Wilson. Since it can be seen with human eyes, in principle, no other detectors are needed, although in practice, all professional observing is done using various kinds of cameras and spectrographs. The image of the astronomer poking his or her eye up to a giant telescope to peer into the sky hasn't been very realistic for almost a century now. So what do we see when we look at the sky using visible light? Of course, stars are obvious, including our own sun. We also see glowing clouds of hot gas. We call these nebulae. Finally, we see sunlight or starlight reflected off of cooler objects like planets. Much of planetary astronomy is done using this reflected sunlight. Radio waves are defined as running from 100,000 nanometers wavelength, or a tenth of a millimeter, up to kilometers. In fact, there is no upper limit to the wavelengths of radio light, although kilometer waves are about the longest we can practically detect. A radio telescope is really just a reflecting telescope. The radio dish acts like the mirror of an optical telescope, focusing the radio waves to a receiver at the focal point. You can see a radio receiver at the top of this telescope, where the four support towers come together. Radio receivers are in some ways much simpler than the sorts of detectors we described before. Typically, they only detect light from a single point in the sky, and at a very narrow range of wavelengths. To create a picture, the telescope has to take a separate measurement of each point. The other thing you notice about this telescope is its size. As we've already mentioned, the long wavelengths of radio waves mean that you need a large telescope to get any kind of useful angular resolution. The largest telescope in the world is the Arecibo radio telescope in Puerto Rico. This dish is 300 meters across. Radio astronomers also make extensive use of interferometry to combine light from several telescopes to improve the resolution. When we look at the sky in radio wavelengths, we see concentrations of gas between the stars, not just the hot gas that's seen at visible light, but also much cooler gas that is invisible to our eyes. In this map of our galaxy, these are the large glowing blobs. The points of light in this map are objects with very strong magnetic fields, especially things like stellar corpses and active galaxies. Both of these produce light through a process called synchrotron radiation, in which electrons spin around magnetic field lines at high speed. This process gives a lot of radio light. Infrared light spans the range from 700 to 100,000 nanometers. This is a wide range of wavelengths, and it means that different parts of the infrared spectrum are best observed in different ways and from different locations, including both ground and space-based observing. All ground-based infrared astronomy requires high, dry locations to get above most of the Earth's water vapor. The parts of the infrared spectrum that are closest to visible light are called the near-infrared. At these wavelengths, telescopes and detectors are very similar to those used in visible light. In fact, often the same telescopes are used for both visible and near-infrared. As we go to longer wavelengths, the equipment becomes more specialized and more like that used in radio astronomy, such as this millimeter wave telescope in Hawaii. Low-temperature objects like planets and interstellar dust emit infrared light. so infrared astronomy is especially effective for observing these. In some parts of the infrared, we can also observe through clouds of dust, allowing us to see into dense star-forming regions, like the one shown here, and along the plane of our Milky Way towards the galactic center. The high-energy part of the spectrum ranges down from 400 nanometers to less than 1 nanometer, and includes ultraviolet light, X-rays, and gamma rays. This is mostly done from space, except for some near-ultraviolet work that can be done from high altitudes on the Earth. As with infrared, the parts of the high-energy spectrum closest to visible light are studied with equipment very similar to that used for visible light, and often with the same telescopes. For example, the Hubble Space Telescope is an infrared, visible, and ultraviolet light telescope. However, as we move to shorter wavelengths, the mirrors and detectors require more specialized designs to make up for problems such as the fact that high-energy photons will simply pass through an ordinary glass mirror. When we look at the high-energy sky, we see a range of energetic processes in space. Ultraviolet light is dominated by the hottest stars in space. However, it's difficult to observe in much of the short wavelength end of ultraviolet light because hydrogen gas absorbs this light very efficiently, and there is plenty of hydrogen between the stars. X-ray light is dominated by very hot gases, often millions of Kelvin, and objects with very strong magnetic fields. This makes X-rays ideal for finding some of the strangest objects in the sky, including black holes and neutron stars. Finally, gamma rays are produced when nuclear reactions happen in space, rather than buried in the centers of stars, or when matter and antimatter collide. Antimatter is like matter, except the charges on the protons and electrons are reversed. It's produced in high-energy reactions, and when it comes in contact with ordinary matter, they annihilate each other and are converted into gamma rays. There are also events called gamma ray bursts. Many of these are produced when a black hole forms from the death of a very high-mass star.
It's important to keep track of what you can see across the spectrum, so fill in this table about observing different kinds of light.
Here are 2 more telescope projects to look at. You should describe the strengths and weaknesses of each of these projects and decide which of the 2 is a better one to receive funding. You should consider the type of light observed, the location, and the match to the objects being studied. Note that there are strengths and weaknesses to both projects, so you should give clear reasons for your selection. The last major property of telescopes is the field of view. This is a measure of how much of the sky is visible at once. It depends on the details of the telescope optics as well as the detectors used. Both large and small fields of view are used extensively in astronomy, and each has its own advantages. Larger fields of view are good for surveying large parts of the sky. If you want to find out all of the stars emitting a certain kind of infrared light in our galaxy, you need to be able to look at as much of the sky as possible in each observation, or else it will simply take too long to do. So an all-sky survey like this is put together from a large number of wide-field images. This is one type of work that small telescopes are often used for, since large surveys usually don't require high angular resolution. However, a small field of view is useful for doing detailed observations on a single or a small number of objects. In this sort of pointed observation, the full resolution and light gathering ability of a large telescope can be used to give a detailed picture of what's going on in a small region of space, allowing us to study the properties of an object like this brown dwarf star. In some cases, the same telescope may be used for both types of observing if there's enough flexibility in the light paths used by the telescope and the range of different instruments that can be used with it. Most astronomy is done using telescopes that detect the light we receive from objects in space. However, there are 3 types of astronomical instruments that might be considered telescopes without light, because they're used to observe other kinds of signals. The first of these is a neutrino detector. Neutrinos are almost massless, and they move at almost the speed of light. They're produced in nuclear reactions like the ones that happen in the center of the Sun. They're also generated in huge numbers in supernova explosions. The most amazing thing about neutrinos is that they only very rarely interact with ordinary matter, which means that they can pass through almost anything. The neutrinos from the Sun's core come right through the Sun without stopping, as well as passing right through the Earth. There are billions passing through each of us every second. They can only be detected by looking for the rare times that they do cause a reaction with an ordinary atom. When this happens, there's a flash of light from the particles produced in the reaction. Several observatories have been set up to observe neutrinos from space, since they're the only way of getting direct information about reactions that are occurring in the center of the Sun. Cosmic rays are mostly protons moving through space at almost the speed of light. Cosmic rays are produced in a wide range of processes in space, including flares from the Sun and shock waves caused by supernova explosions. When a cosmic ray hits the Earth's atmosphere, it shatters and produces a shower of smaller particles that come crashing down towards the Earth's surface. There are two ways of finding cosmic rays. One involves using particle detectors on the ground that get struck by the shower of particles. The other uses telescopes designed to find the flashes of light as these particles break up in the atmosphere. The last kind of lightless telescope observes gravity waves. A gravity wave is a wave in space and time, making distances oscillate between stationary objects. The first gravity waves were only recently detected. It's hoped that in the next few years many more will be found. Gravity waves are produced when very large masses accelerate rapidly. The ones we've seen so far were produced when two black holes, many times more massive than the Sun, crashed into each other, creating ripples in space that spread out for billions of light years distance. The way to detect gravity waves is by looking for these vibrations in the distance between 2 points. This picture shows a gravity wave observatory in Washington state. The distances along the two arms are measured with very high accuracy to look for the evidence that these ripples in space are moving past the observatory.